computer graphics and in English. It's the summer term 2025 at the Bocholt campus of Westphalian University of Applied Sciences. Lots of people sitting here for computer graphics, some people, lots of people being online. We have an exchange student in the course, so the language will be English. Language from my side will be English, at least I'll be trying to do it in English. The people here can ask in German, the people on the Zoom meeting can ask in German. I will translate it, and we all need to figure out how we go through it. This is computer graphics. This is not pre-recorded lectures this run, because I rearranged the topics and was not able to do recordings for the stuff that I'm going to tell. So this is, maybe a proper or typical lecture. I will do the stuff here in the room, and we'll not be able to provide the content before. You will find the handouts online to take notes, and since I'm still rearranging the topics, please allow me some more time to prepare the handouts for the remainder of the course. I think I already added all the topics, at least the headlines, in the Moodle course. That should be available to all the students. If you're, for some reason, watching this on YouTube and not being a student here, you also find the course material online at the website of my work group. All right, but there should be a link in the video description. Anyway, anything to be discussed prior to me starting to talk for hopefully not so long a time? All right. Then let's start with the intro to the introduction part. And yes, it was clear that this one pops up on the screen where it's not supposed to be. And there is the screen I need here, and my slide preview is on the proper screen. All right. Should work. Who am I? Tom Vierjahn, born 1981. And I studied also at the University of Applied Sciences, Media Technology in Düsseldorf. I did my diploma back then, while this was still possible there, and afterwards I did a master's degree also at the University of Applied Sciences in Düsseldorf. The diploma was Media Technology. Afterwards it was called Virtual Reality, so lots of computer graphics in the study program. And afterwards for my PhD it was still computer graphics, more geometry reconstruction at the Westphalian, how was it called? No, they call University of Münster right now, so it got a bit easier lately. I did my PhD in 2015 on geometry reconstruction. That is also computer science and computer graphics related. And for work, I started as a research assistant at the place where I did my diploma and my master's thesis, and afterwards for the practical work during the PhD time, I went to RMH New Media in Cologne, a company that was back then doing virtual reality and interactive computer graphics, but also some web stuff. For the postdoc phase, I went to the virtual reality and immersive visualization group of Professor Kuhlen at RWTH Aachen University. And since 2018, September 2018, I am here for the introductory courses on computer science, and also, still colorful images, so it's still computer graphics 1, 2, and human-computer interaction. All right, what is to be expected from this course? We're going to talk about images today after the introduction. Then it's going to be ray tracing. That is one of the topics I shuffled. Earlier I was doing it in the second course on computer graphics in the winter term, but I think it is a bit more straightforward to understand than doing rasterization. computer graphics started out doing rasterization, so I thought in Computer Graphics 1 it would be a good idea to do rasterization or the traditional graphics pipeline, but ray tracing is simpler to comprehend, but computationally far more expensive to do. But anyway, you'll see it. Then we do illumination from the perspective of ray tracing, which will still be applicable to rasterization or the traditional graphics pipeline. The same applies to transformation. Hopefully we come to animation and do some time-dependent stuff. So not going so much into the aesthetics of animation, but what this means for, bring time into the picture. And then we, do this all from the very beginning, once again, for rasterization, but this will be just a quick recap, adding projection and viewing to the mix in the end. All right. What does this get you, or what does that mean for you? When successfully finishing this course, you will be awarded 6 credits for your study program, and I think this should be the same for the exchange students. By the way, is it only one, or do we have both here? Anyway, just see one, it doesn't matter. The course will be split a bit, 1.5 hour lecture and 1.5 hour a practical part. This will shift a bit. I think 1.5 hour from me will be the number for today, but in 2 weeks, I don't think this will suffice. I have a bit more to say for ray tracing, but we'll see. This is going to be in person in the computer lab. It's possible to join remote via Zoom. Some people are already there. The link, by the way, is in the Moodle course. You can sit here and do this live and in person, but you can also do this via Zoom. If the internet holds, or the internet connection holds, I will stream it live via YouTube, but it will be recorded and made available there afterwards. And then the second half, the practical part will be a rather traditional practical course at the beginning. I have some assignments for you that you will hopefully try and program and finish. And afterwards you will be shifting towards the project work that you decided to do in a group. And I've prepared some topics, but we'll discuss those later after we've done the image part. This will work basically the way I provide the basics or the fundamentals. You can dive into the subjects further in the project work. So if I talk about illumination in terms of ray tracing, you are very well invited to do global illumination or stuff like that. So I provide the fundamentals, what is illumination, and you pick further topics, means then you could do global illumination. But this is a terribly bad example for the projects I prepared, but yeah, you'll see anyway. Any questions so far? Okay, not yet. We'll see. At the end, there will be an exam. That is not a written exam. All the people that already did some projects with me know about this, that you will have to do a talk and a project demonstration of the stuff that you did during the semester, and then also hand in a written report about the stuff that you did. This should be some sort of scientific-y or scientific-ish talk and report, meaning I rather do not want to see in this and that code file, line 200 and whatnot, I write this statement, then there is a semicolon, and then I start a new class, and there is another class, and here yet another one, and a UML diagram, just for the sake of providing the code of the UML diagram. There's no use in doing that if you want to provide anything in the direction of a scientifically written report. This is just a report of steps that you did. I would rather have you work on a topic that you select and then talk and write about this topic, meaning that you provide an introduction, and this applies to the talk and the written report. You provide an introduction outlining the problem, narrowing the problem down to the manageable part that you will do during the semester, then looking left and right, what has already been done by others, related work, then talk about the stuff that you did, but not the individual steps that you have taken, but rather the overall picture. What is this all about that you are doing? What is the experiment that you're conducting? And not how do you build the tools that help you do the experiment. Then you provide the numbers and discuss those and put them into the greater picture, provide some future work, and this is basically the outline of both the talk and the written report. Concerning the language, you can decide whether to do it in German or English. I have no preference there. It's basically up to you what you prefer. Do it in German, do it in English. Yeah, and I will read it. Okay, the talk and the demonstration will most likely be in the first week of the 2 examination weeks at the end of this semester, so approximately in the July timeframe. And the written report will have some more time. You can do all the other exams first and then have about 2 weeks to finalize the report and then hand it in via the Moodle course. Does that sound like a plan? Okay. You should be working in groups. Approximately 4 participants are a good number. You shouldn't have to do it alone, but if you want to do it alone, I won't forbid it. I don't recommend it, but we're all computer scientists and other people and stuff and all the cliches. Yes, I know about them. Anyway, right. Some recommended readings. The Fundamentals of Computer Graphics has pretty much everything in it that you need to know for this course and much more. I don't know if the library down there has some printed copies of the book, but the university paid for an online edition, and if you are logged into the university network, basically being here in the EduRoam Wi-Fi or accessing the network via VPN, you can freely read this book. There are some special means of printing this stuff or downloading it to your machine. There is a quota on that. So if you decide to print the book, you want to take a printout of the second page and another one wants to print out the first chapter, there might be a problem because there are limits to it. So better read it online and excuse the suboptimal interface to the book. But somehow digital letters tend to erode or need some maintenance. I don't know why they want to make so much money, but anyway, someone has to pay for it, and I'm glad that we bought the online edition, and it should be possible to read here from the university network. The book I learned ray tracing from is an introduction to ray tracing edited by Andrew Glasner. Pretty much the first chapter explains everything you need to know for the ray tracing part in this course. If you want to go further, is it the first? Maybe the first 2 chapters. But if you want to do more complicated stuff, read the remainder of the book. It is pretty approachable, I think. And even though it's from 2002, it is still on point if you want to learn ray tracing. If you want to go all the way to the real thing, look at physically based rendering. But maybe take the physics and the math course that we offer first. but there you go all the way down to maybe not individual photons, but you do lighting the correct way. You look at the spectra, you look at the amount of light that you are able to collect at from some direction. You will need some integrals to do this. You will need to have some physics understanding, but they implement it properly. The book is freely available. It was not freely available, unfortunately, for quite some time, and it was pretty expensive. But anyway, it's I don't know if it's open source, but you can just read it online. You can still buy it if you like. But yeah, there is a PDF that you can read online. And if you want to go into the traditional rendering stuff with rasterization and the rendering pipeline, you may want to have a look at the real-time rendering book. But yeah, this rather goes beyond what is in the fundamentals of computer graphics. All right. What is this all about? Why don't you see it? Guys, this is strange. I'm looking at my presentation, I'm showing you the slides, at least I think I'm showing you the slides, and all you see is green. And all that you on the Zoom meeting see is me standing in front of this green screen. Who of you have noticed that something is a bit off? Thanks for not telling me. That is the slide I wanted to show you right now. Anyway, I think the other slides are available in the handout. I don't think I left some blank lines in there for you to fill out. But please, if anything goes wrong, or you think I should be showing something that I'm actually not showing, please tell me. Okay, what is this all about? It's a picture from 1525. I don't know if the picture itself is by Albrecht Dürer, but it's in a book by Albrecht Dürer. What do you see? And just as an explanation, I need to switch the camera back to the camera to show it. I have this microphone that I can throw at the people who are sleeping or want to talk, so that the people in the Zoom meeting can also hear the guys here. And if other people than me are talking, I'm going to mute my microphone that only my voice is in the stream and in the recording, and you are safe to say anything that you want. So, what do you see? And now I'm going to mute me. Okay, just do the audio for the stream. There is a painter painting a picture from another man, of a picture of another man. And what does he do? How does he paint the picture? Just throw the cube mic to the other people. Exactly. He's looking through some eye thingy where he can put his eye to have always the same perspective on the scene. And then he's drawing, maybe he's drawing just the outline of the man sitting in the chair and then coloring it later. But this having the eye at a fixed location, we need this in 2 weeks. But what he's doing is putting what he's seeing onto the glass surface. And it's pretty much the same that we will be doing here in this course. We are going to synthesize images. We don't have the real scene that we can draw, but we have a virtual scene that we want to draw. Not on a canvas or on a glass, but on a virtual canvas. And we want to create images from something we have in the computer. All right. This is just the introduction. There's more to come. We talked about, or I talked about, and I intended to show you slides about who, what, and how, and the reading material. Anyway, you'll find it in the online material, so you can read it later. And I hope that I at least provided some little overview on what we are doing this for. Right. Any questions so far? All right. Then let me just switch the slide deck to the second part. Let me just grab, where is it? No. I need the preview to know what I will be talking about. There it is. That is the screen for the backdrop. Just to make sure you're seeing the slides, right? Okay, good. We'll be creating images. Back to this picture. What are images? Just think about it for a moment and then tell me. And by the way, if you are in the Zoom meeting and want to say something, just raise your virtual hand and or maybe just talk. I muted you in the on the speakers, but I still have these headphones on, so I can hear you. And if I don't see your virtually raised hand, just talk to me, and yeah, I can give you the word. So think about this picture and tell me, what are images? All right, hand the microphone over there. All right. We had everything. Let's just do some sort of, it doesn't work. Let's do some sort of definition. It's everything in there that you've written and just said. 2 dimensions. And it records intensities. Yes, there are separate areas in the images that are of similar intensity, but we all right. For the moment, I think we just need its 2 dimensions. We can have 3-dimensional images, but that is maybe some special applications that we need 3 dimensions for. And we record intensities. Whatever intensities might be, we come to that later. But it's a 2D recording of intensities. All right. That is the eye, the human eye. What is it? Is it made up of? What components does it have that are maybe related to images? There's lots of stuff in the eye, but some important things, or some things that are important for images or for perceiving images. You said there is the retina, there is the lens, and then you set the iris, and then of course there is the pupil, because we need the slot for the light to enter the eye. With the cornea, this looks like just transparent stuff, but it is a major component of the refractive system of the eye. So this does nothing. And the retina is basically just the sensors for the light that are all gathered into the optic nerve and fed into your brain for you to see stuff. Okay? On the retina, you have rod cells and cone cells. The rod cells are just light sensors, just for intensities. That are the Stäbchen in German. They just tell you if there is light, and if so, how much. And then there are the cone cells that are responsible for color vision, that are color sensors, basically. But there is the difference that the rod cells just need a low lighting level, whereas the cone cells need much more light. And the cone cells are the Zapfen in German. Right. You said there are cones for red, green, and blue light. Depending on whom you ask, it doesn't have anything to do with colors. I'll show you why. It's closely related to colors, but it is not colors, it is different wavelength. And this might be a tiny difference. I'll show you on a diagram later, but this is important if you want to do it physically correct later. There is the S cones, the M cones, and the L cones for short, medium, and long wavelengths. But yes, of course, those three different wavelengths are related to colors, and that is why you typically draw them red for the long wavelength, green for the medium wavelength, and blue for the short wavelength. But primary red might be a spike about here, and just a spike. Everything else than this spike is not red. It's reddish. Especially if you look at this part of the diagram, the L cone works with green light. It does also work with blue light. But it has its absorbance peak definitely way in the red part of the spectrum. So yes, this is the red sensor, but it is sensible to every wavelength. The green one does not so well for red light, and the blue one doesn't do any red light, but still green. And that is why I said, depending on whom you ask, those are not color sensors. They react to different wavelengths, but of course the wavelengths are related to color, and the peaks are at red, green, and blue. And since there is a red color sensor, and I'm doing it myself, a red color sensor, a green color sensor, and a blue color sensor in our eyes, it might be a good idea to say color consists of red, green, and blue. And just red, green, and blue. And we can go pretty far by mixing those. And if we say the red color is such a red that we can trigger the L cone, if the green is such a green that we can trigger the green cone, and the blue is such a blue that we can trigger the blue cone, we can decide which cone to trigger how much. And therefore we can decide or control which color we see by just going red, green, and blue. Okay, if we mix red and green, what color do we get? Careful, additive color mixing. Because we have red light plus green light entering our eye. We're not painting a picture where we subtract red and green. We get yellow. Mixing red and green turns out yellow. What about mixing green and blue? Cyan. Yeah. Blue and red. Yes, magenta. And then having everything in there. The color that isn't a color. Yes, white. And the center is white. If we mix everything, we have white light. Right. Questions so far? So images record intensities we're seeing with our own eyes, and most people can perceive colors properly. And if they're perceiving colors properly, they have 3 working sensors for different wavelengths that can be thought of as a red, green, and blue sensor. And if we have separate channels for red, green, and blue in our eyes, we can trigger them from the outside to perceive any color. And we can do this by mixing the colors additively. So we have a three-dimensional color space to choose from. If there is no color at all, we're black. Going in one direction, we get redder. Going in the other direction, we get greener. And going in the third direction, we get bluer. Let's start with a vertical one because it's better to see in this picture. We're moving from black, no color at all, adding more and more green intensity, we're getting greener. If we do it on the back plane and on the side plane of this cube, we can move from black to red, from black to green, from black to blue, or we can go from black to red-green, aka yellow, from black to green-blue, aka cyan, or anything in between. And if we add, what are we missing? Everything up, we can go all the way up to white at the topmost corner, and everything in between. Just mixing three colors. Okay, so going back to the images, slightly more accurate. And now we're taking your pixels, because we're on a screen, we just have discrete points where we can show the color, but we have three colors to show on each pixel, short for picture element, by the way. We can represent it in code in the computer to create a program that deals with images. How would you do that? If you were to do it, for example, in C. We're having groups of 8 bits. You say we're having 4. And if you have groups of 8 bits, they can be easily printed in hexadecimal. Because 8 bits make 2 hexadecimal digits. Therefore, it's convenient to do it in hexadecimal. We obviously need a channel for red, we need a channel for green, we need a channel for blue, because we have those sensors in our eye. We can add the fourth, the transparency. But we don't need this so much at the end of the screen, because we can't make the screen transparent. We can use the transparency if we are to layer images, to say, okay, we have a topmost image that is semi-see-through, where we can still see the stuff that is underneath. Then we need the transparency to layer them. But just for creating the final image that is composited of all the layers, we just need the 3 final colors, red, green, and blue. In the simplest form, as 8-bit numbers, 3 of them. So a 6-digit hexadecimal number. And if you were to program it, you could do this as unsigned integers with 8 bits of width. You need 3 of those guys, and you need them for each pixel along the width and along the height of the image. Okay, and the uint8t is just a data type that the standard library provides to guarantee that each integer is 8 bits wide. You could still use the traditional integer, then you store 16 or 32 bits per pixel, but this doesn't matter for this course. All right, if you were so fancy that you say, okay, 3 groups of integers have a meaning, I combine them into a color data type where I don't need to address them just by the array index, but I can rather say, okay, I need the red.red.r or whatever, the red channel, the green channel, the blue channel. You would want to create a color data type, just a struct or a class or whatever, and then you just have a 2-dimensional array of this with a third dimension hidden in this guy. Okay? But that is something that you could code away just now in a few lines of code, being it C, C++, Java, Python, you name it. It would look pretty much the same in all of those languages from the structure. All right. How to store those? In a format that you can look at. Because this is just the internal representation in the code that you will write. But you want to open it in, say, GIMP or Photoshop or any image viewer that supports an image format. What do you need? What are you typically opening in Preview, Paint, Photoshop, GIMP? What are those guys that you're opening there? This is not an array of uint8t's, right? There's something else. Okay, you could choose a JPEG, you could choose a PNG, a TIFF, or basically whatever. Any file type would be suitable to store it. If you created the image in your code, you need to store it on disk to later view it. Or you write the image viewer yourself, but it would be easier to say, okay, I can just dump all the bytes into a file in the proper format and then open it in the image viewer. How to implement JPEG? Yeah, libjpeg apparently. What about TIFF? libtiff, the same applies to PNG, but you need the library, you need to look at the API, do the syntax and all the stuff. JPEG has all this compression thing. GIF does offer you animations, but how to deal with the animations. PNG has also some compression, but also lossless and lossy compression. TIFF is the raw bytes, but there is the resolution, and they have fractions of sizes, and it's just complicated. There is a simpler format. A very simple format that you could even write in a text editor, and that is the portable pixel map, PPM. There is a Wikipedia entry for this, and you can read the specification in there and really write it in your editor. And since you can write it in the editor, you can probably just dump it from your program with printf or stream output or whatever, and be done with it. A little caveat, you need an image viewer for it, and Windows without another image viewer is not it does not open PPM images. You need an image viewer like OpenView. macOS can open those straight away. I don't know how the situation in Linux is, but there are free image viewers that can open PPM files. And this is basically the format of a PPM file. You have a plain text header with a magic number at the beginning, and then the width and the height written in plain text. Not a binary bit field, but if you have a 480 by 640 image, the width will be written out as 480 space and then the height 640. And that is something you can read in the text editor. The next line says how large can the number in each individual channel be? And a simple way would be 255 because that just fits into 8-bit. And this just defines this is an 8-bit per channel image. So if you have red, green, and blue, it's a 24-bit per pixel image. And yeah, then in a ppm file, you just dump the pixel values one after the other. First pixel, red, green, blue. Second pixel, red, green, blue. Third, and so on. You don't even need to care about line breaks. And you don't need a special library to do this. You can just dump it with printf if you decide to do so. And there is just one thing to consider. Do you want to dump the binary values? Then better don't do it with printf because you don't want to see the digits. You just dump the 8 bits to the file. Or, and then coming back to editing the image file in the editor, you use P3 instead of P6 in the header. And then you can just dump ASCII numbers and have the image just in plain text. It's horrible in terms of compression. But anyway, it's a very simple image format that you can just write straight out of your application and view in an image viewer without having to deal with an image library or doing a window API or whatever to have the image visible in the browser. Okay, good. What have we done? We've talked about the human eye, colors, images, and a simple image format for you to use in the first practical assignments. Okay. Questions? Okay. The question was, is ppm being used? Let's check. ppm image. NetPBM is the overall name. Oh, the stable release. Interesting. Where is it? There we go. So it is part of the NetPBM open source package. The last stable release is just like a month old. Interesting. Still gets updates, and it defines the file format. We're looking at portable pixel maps. We just, because we're doing colors, we're not doing black and white, and we're not doing just grayscale. And it's basically, yeah, a very, very simple header with just a dump of the values they want to have in there. All right. Extensions, 32-bit programs. History. There's the history. It's from the mid-1980s. anyway. If you're doing proper imaging, you probably won't use those because, yeah, the compression ratio, practically non-existent. But if you just were to dump images, it's pretty easy to dump them and pretty easy to read them and work with them. Yeah. Yeah, apparently. So you were talking about a full HD picture, 1920 by 1080. 1920 is approximately 2K. 1080 is another 1K. So you have 2M bytes thingies in there. Times 3, it's 6M things in there. Times byte, it's 6 megabyte. If it's the binary variant, if we say, okay, then coming back, we have 6M entries, each 3-digit long. It's 18 megs of plain text plus the white spaces in there, 30 megs for just one full high definition image. That is uncompressed image data. Easy to read, easy to write, easy to work with. Right. 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 Doors have handles sometimes, sometimes not. Anyways, okay. So another uncompressed image format would be TIFF, but it's harder to write because the header is more complicated. In the end, it boils down to also just dumping the binary data of the image, but you need to provide a longer header. You could go uncompressed in TIFF, and I think just doing PPM is the most straightforward way out of your application. With just having studied like 2 weeks here in the program that you were doing, when you should have done all the output functions in the computer science class that you need to write a proper image to disk that you can open in Photoshop. Okay, now we're talking about generating those images. Okay, questions so far? So the content of the lecture, images and generating them, and what are they? How do we see? All right, then. That was the official part that goes into the recording. We stay in the Zoom meeting and here, and then we can talk about the projects. But yes, this was the first part of computer graphics. I need to get the numbers straight. The first part of computer graphics in the summer term of 2025 at the Bocholt campus of Westphalian University of Applied Sciences. Thanks for watching. See you later.